All right, so starting off with the topic of sound waves, right? Now, we have already discussed that sound waves are your longitudinal waves. Okay? Now, uh, and we had discussed the properties of longitudinal waves as well. How do longitudinal waves work? Just to revise, if you remember, a longitudinal wave is a wave in which the particles vibrate in direction of the wave travel, or to make it a bit more accurate, the particles vibrate parallel to the direction of the wave travel. That's what I had told you. And it is composed of refraction and rarefaction. So sound waves are longitudinal in nature, right? The particles are going to be oscillating in direction, same direction as the wave travel. So if the wave is traveling from left to right, okay? If the wave is traveling from left to right, what is going to happen? That the particles are going to be vibrating in the exact same direction. And this is what a sound wave, this is basically what a longitudinal wave looks like. Okay. Now, we had discussed that this is the compression. Compression is an area of high pressure. The reason it's an area of high pressure is because all of the air molecules, or whatever the medium is, the sound is traveling through water, the sound is traveling through air, whatever the purpose is, the particles are all pushed together, right? So that creates a high pressure. Then we have a rarefaction. A rarefaction is an area of low pressure. That is because the particles are all spaced apart from each other. They're all far away from each other. Now, in a sound wave, we had discussed a wavelength, right? A wavelength can either be from one center of one compression to the center of the next compression, or from the center of one refraction to the center of another refraction. That's the wavelength, lambda. That is something we had discussed previously. Now, what are the properties of waves that I had taught you? I had taught you reflection, I had taught you refraction, and we had gone over diffraction. Now, sound waves are going to give you similar they give you similar results. Okay, sound waves can be reflected, sound waves can also be diffracted, and sound waves can also be refracted. So let's go ahead and take a look at all of these properties one by one. The first property that we are going to go ahead and we're going to talk about is reflection. Okay, now you have already studied reflection. You know what it is. Reflection is when a wave hits any reflective surface and it is bounces back, right? It hits the reflected surface and it bounces back. The angle of incidence is always going to be equal to angle of refraction. Now, for a light wave, it is easy to understand exactly what reflection is going to look like, right? For a light wave, it's so easy to understand how a reflection looks like. The reason for that is because we see our reflection every day in the mirror. So we know exactly how the light hits the mirror and rebounds back. But sound wave reflection, where have we studied it, or where have we heard it, or how is it actually used? The way it's used is in the sonar system or the radar system of the ships. So you have your ships that are going onto the surface of the water, right? How is it that these ships, how is it that the submarines are able to tell what is in its surrounding, right? How is a spaceship, how are the people sitting inside the ship, is sitting inside a submarine able to tell exactly how far away something is? How are they able to tell that something is approaching them? How does the radar system work? So the radar system works on the principle of sound. Okay, let's imagine we have our ocean. Underneath the ocean, we have the ocean bed. Okay, on top of this, we have a submarine that is, sorry, yes, it's submarine. We have a ship that is moving across the surface of the water. Now, what is going to happen is this, that this machine, this ship is going to emit sound waves. Okay, that machine is going to emit sound wave. As it is going to emit sound wave, that sound wave is going to travel down through the water, hit the seabed, and when it is going to hit the seabed, it is going to be reflected back to the surface of the ship. Okay? Now, what does the ship do? The ship is going to detect the time between emission and receiving. So the ship is basically the person who's doing who's managing the ship. They're gonna say, okay, we sent out a wave at time. Was the time when I sent out the wave. It took this many seconds for the wave to come back to my receiver, right? Once they have noted down the time, what are they going to do? They know the speed of the sound wave, right? The people who are running ship, they know well enough what is the speed of the sound wave. Just like if you remember, I told you the speed of light is fixed in air. If you remember, I had told you it's always 3 into 10 raised to the power of 8. Similarly, the speed of sound is always fixed. In air, the speed of sound is always around 340 meters per second. Okay. Similarly, the speed of sound in water is known. The scientists know exactly what the speed of sound in water is. So they know what the speed is, right? They know what the time is. They know how long it took for the they know how long it took for the wave to come back. So they know what is the time taken. So they know the time, they know the speed, they can use it to find the distance. This distance is then going to let them know how far away the object is from the submarine, from the surface of the ship. This is how they're able to prevent collisions. This is how they know, oh, we're now entering into shallow water. We have to be more careful. The ships can get damaged, the submarines can get damaged, we can have a collision, whatever. So regardless, this is how a reflection works when it comes to your sound waves, right? Now, one thing that you and I both have to realize. What's that one thing that you and I both have to realize? When I am using the time, I have to realize that when I am measuring the time, so when I'm measuring the time, I am measuring, this is T1 and this is T2. Okay. So I want to find out how long it takes for the wave to travel. So I can do T2 minus T1, right? And I can find out the change in time. I can find out how long it took for the wave, the pulse of sound wave to come back. When I emitted the pulse of sound wave, how long did it take from the emission to the receiving? When did I emit it? When did I receive it back? I can use it to find out the time. How long did it take for the sound wave to come back to me? But you do realize that this time is for the wave to go down and also for the wave to come up, right? This total time that you're going to find, this time is going to be for the wave to go down, hit the ground, and then come back up. When I want to find the distance, what distance that is it is the which distance do I want to find? I want to find the distance of going down. I want to find out how far below is it. I want to find the distance of going down. So when if this is the distance d that I want, okay, this is the distance d that I want to find. But the time taken that I'm using for calculations is for the total journey, for the sound wave to hit the ground and also for it to come back. So we have to remember that we have to divide the time by 2. Okay, so we can find the time it took for the wave to travel one way. So this way I will know how long it took for the wave to travel one way, to either go down or come back up. Doesn't matter. But I'll find out what was the time taken for the wave to go one way. And this is the time that you guys you will use in the formula. The reason I'm explaining this in detail is because you do get questions on this. You get questions where they give you the sonar system, a diagram that looks just like this. They say it took this much time for the wave to be received back, calculate how far away it was. So you have to remember in that situation that the time that you have is for the whole journey. You have to divide that by 2 so you can find out how long it took for the wave to go down and hit the ground. That is the distance do you want, right? This total time, this time that you're going to have, this time is for the wave to go up as well as to go down. So we have to divide it by 2 to find the time taken for just one journey. Making sense?
Um, kind of.
Let me go
I
over it
just
again.
like
Yeah. Yeah,
I
yeah.
just don't know how like it has something to do with sound. Is it like the sound traveling?
Yes, it is. They are literally emitting a sound wave. Okay? They literally emit a sound wave. This is not a light wave, right? This is a sound wave. They emit a sound wave, and that sound wave travels through the water. That sound wave is going to hit the surface of the seabed. That sound wave is then going to be reflected. Remember, reflection is a principle that applies to everything. It applies to sound, it applies to light, it applies to the waves in the water, it applies to the waves in the earth. So every single wave undergoes reflection. Okay. Similarly, sound waves also undergo reflection. So we don't emit a light wave because what happens is that, think of it this way, that the deeper you go into the sea, right, the less and less light penetrates through. So light is not a very good way of detecting or seeing how far away something is, right? I can shine a light over here, but that light is not going to reach deep enough for me to see what I want to see. Similarly, this is just a seabed. Imagine you are in a submarine. You must have seen in the movies, they have that radar system, right? And if something, often in your science fiction movies or action movies, if somebody comes to attack, they see it on the radar. Oh, there's something that's coming to attack. So one of the ways that thing works is that, so they don't use light waves, right? Light wave is not going to go deep enough. Sound wave travels very well in water. So what they do is that they emit pulse of sound. They send out sound waves. So imagine that there is a speaker and it's repeatedly sending out small pulses. Okay, so like a small sound, then stop, small sound, then stop, small sound, then stop. Okay, so the sound wave is being produced. That sound wave travels to the bottom of the seabed. When it hits the seabed, it gets reflected back. It gets bounced back because it's a wave. All waves have same properties. So it gets bounced back. As it gets bounced back, so it travels back up through the water towards the ship. The ship has a receiver. That receiver picks the sound wave that we have received the sound wave back. And the sonar specialist will note down the time taken, that I sent out the pulse of wave at this time. I received back the same pulse of wave at this time. So how long did it take? He finds the time taken, you divide it by 2. We already know what is the speed of sound in water. It's a well-known fact. So they can simply calculate what the distance is. Okay, so sound wave, the reason we are using sound wave is because sound waves travel better in water compared to light waves. That's why. Okay. So they just, the ships, the submarine, they just produce small pulses, burst of sound. Okay, the sound travels around as soon as it hits something. For example, another submarine comes close to yours. Okay, so what's going to happen? The pulse of sound is going to hit that submarine because now it's close to ours, it's within our range. It will hit the submarine, it will be reflected back to my ship. And when my ship is going to detect it, my ship is going to be able to calculate the time taken, how long did it take for the sound wave to come back, and we will even be able to tell how far away it is from us. Is it a bit more clearer now how the reflection works?
Yeah.
Okay, great. So, but the main thing you have to remember for your calculations is you have to divide the time by 2. Okay. The time that is given to you is for the entire journey. Okay. Now, another property of sound waves that we have to understand is obviously refraction. Okay. Now, when we talk about refraction, what is refraction? Refraction is that refraction, you already know what refraction is. You know that refraction is that as you go from one medium to another, what happens? As you go from one medium to another, the speed of the wave changes. Okay? The change in the speed of the wave causes the wave to bend. Fine? Now, that's refraction. Sound waves definition is the same. Please keep in mind, definitions do not change. The way it is observed might change, but definitions themselves will not change. Okay, definitions remain the same. So the same principle that we studied for light, sound follows the same principle. If a sound wave travels from air to water, the speed is going to change and it is going to refract. Now, let me give you an example of refraction that you might have possibly noticed in your everyday life. Okay, so I don't know if you have ever noticed this or not, but what happens is that in summer, you will notice that the sound coming from the outside are not that loud, right? If you live close to the roads, the sound of the vehicles is not as loud. If for example you have a mosque nearby, so the sounds that you get, the adhan, it's not that loud, right? You go on to your winter. In winter, the sounds that are coming from the outside, they appear to be a bit more louder. The azan appears to be a bit more clearer. The sound of the vehicle coming from the roads appear to be a bit louder. Now, normally we use, at least we attribute it to the fact that, you know, we normally in the summer, we have air conditioners and everything going on full blast because it's so hot. But that's not the reason. The reason is that sound waves, the reason is that sound waves actually, believe it or not, sound waves travel faster in um, warm air. Okay, when the air is warm, the sound wave is going to be is actually going to be is actually going to be travels faster in warm air. Okay, the sound travels faster in warm air and it travels slower in cold air. Okay, so sound actually travels faster in hot air or in warm air. and it actually travels slower in cold air. Now, normally what happens in winter is that the air that is on the ground is a bit warmer, right? If you compare the air towards the surface of the earth and the air that's slightly higher up, there is a difference in temperature, right? The air that is slightly higher up is a bit the air towards the bottom, right? The air towards the bottom is a bit warmer. The air towards the surface of the ground. As you go higher up, the air becomes a bit cooler. Now, what happens? What happens is this, that as the sound wave, so let's say you are standing over here and you're talking to your friend over here. Now, what happens? What happens is this, that the sound wave, and this is the sound wave, it's going to travel. Now, when the sound wave is traveling through the warm air, it's going to travel very quickly towards your friend. But this is a sound wave. The air molecules don't just travel in one line, right? The air molecules are going to go everywhere. So what's going to happen, that some of the sound wave is going to travel in the warm air. But some of the sound waves are going to they're going to move from the warm air to the colder air. When they move from the warm air to the colder air, there is a change in speed. And whenever there is a change in speed, the sound wave bends. That's refraction, right? In refraction, there is a change in medium. Over here, the medium is pretty much the same, but the temperature changes. So we can say that the medium is changing a bit. So what happens, that the speed changes. In refraction, when speed changes, the sound wave bends. Any wave is going to bend. So what happens is that in winters, generally, we have a mix of, like a bit of warm air at the bottom and then we have cold air. What happens is that when the sound waves travel from the warm air to the cold air, they are going to undergo refraction. When they're going to undergo refraction, why are they undergoing refraction? Because sound travels slower in cold air. Okay, since sound travels slower in cold air, so it's going to take a bit more time to reach. So speed changes, it will refract and it will bend, right? So over here, your friend is going to receive two sound waves. First, she will hear a sound wave coming through the warm air, because from the warm air, the sound travels quickly. Now, the same sound is also going to refract and reach your friend from the cold air. But that will be slightly delayed. Okay, that will be slightly slower, but slightly, not too much. Slightly slower. Okay, not too slow, slightly slow. So what happens is that the sound your friend is going to hear is going to be louder, because she is receiving two different sound waves. Because she is receiving two different sound waves, so you are going to appear louder to her. This is an example of refraction that we see with sound waves in everyday life, right? In everyday life, this is what happens. So this is exactly what happens. So this is an example of refraction. The sound will travel quickly through the warm air, but when the sound is not different, right? The same sound, when it travels through cold air, it's going to become slower. The change in speed is going to cause it to bend. Hence, the person is going to hear, the voice is going to appear slightly louder, because they're receiving two different sound waves. Making sense somewhat?
So they would be louder in like hot air
Yes.
and quieter in cold air. So like,
Yeah.
so what if you're like between the two? Like, what if like you're in the middle?
If you're in the middle, it will probably still appear louder, right? Over here, so when you talk about it's not always that. Okay, so when you talk about air, the thing about air is that it's not the same temperature throughout, right? uh if the air towards the surface of the earth is generally warmer, you are going to go up to the mountains, the same air becomes a lot more colder, right? So the thing is that air is a very subjective thing. It's never completely cold, it's never completely hot. It is always going to be a mixture of. Okay? So, but if it's quite hot, like in summers, so the air is going to be all warm, right? Since the air is going to be all warm, so the sound wave will just, there won't be any refraction. The sound wave will just travel as it is. If it is completely cold, again, in completely cold, if there is no warm air, again, there is going to be no refraction. But generally, if we talk about, generally where we live, even in winters, we have a bit of a mixture, right? It's not completely, not all the air is always going to be cold. Not all the air is always going to be completely hot, right? Generally, we see a mixture. Some of the air is a bit hot, some of the air is a bit cold. So that is, this is what happens in those situations. Clear? Making sense?
Uh, yeah, yeah.
Are you sure? Do you want me to go over it again?
So like the only thing I need to know is that like it
Yeah.
travels like slower in cool air
Yes.
and like it
And faster
travels
and
faster in hot air or hot air.
yes. Yes. So when the sound is going to go from hot air to cold air, it will refract. That's the thing. That's the thing you need to understand. That when the sound goes from cold air to hot air or from hot air to cold air, it will refract due to change in speed. Okay. Now, do you remember that in the light wave topic, we had discussed that as the light moves from less dense medium to more dense medium, right? The speed decreases, right? That's what we had studied. In sound wave, it's slightly different. Okay. In sound waves, what happens that in sound wave, in air, the speed of sound is 330 to 340 meters per second. You need to learn these values, by the way. In water, the speed of sound is around 1400 to 1500 meters per second. Right? So the one second.
Is that 1,400 to 1,900?
Yes, exactly. In glass, the speed of sound is approximately 4,000 meters per second. You don't have to learn it, just letting you know. Sound is different. In light wave, what happens that as the light travels from a less dense medium to a more dense medium, it becomes slower. Okay? As it goes from less dense medium to more dense medium, it actually becomes slower. Okay? Now, what happens to sound wave? Sound wave is the opposite. Sound wave, as it travels from less dense medium to more dense medium, it becomes faster. That's one point that you have to remember. When I taught you the topic of light, so keep in mind that refraction is not going to change. Okay, Sasha? Refraction is going to remain the same. Refraction is simply the bending of wave due to change in speed. Now, in light, when you go from air to glass, the light wave slows down. That's what I had taught you. Remember that when if we talked about light, so as it goes from less dense, which was air, to more dense, that was water or glass, it will slow down. That's what I had taught you. And because it will slow down, it will refract, it will bend towards the normal, right?
Yeah.
Sound wave is the opposite. When a sound wave goes from less dense to more dense, it actually becomes faster. Again, the speed is changing. For refraction, I only need the change of speed. Since the speed is changing, it will refract, but it will actually refract away from normal because the wave is getting faster. Right? So remember this. Light is faster in air. The same light, when it travels through water or glass, it becomes slower. Sound wave, on the other hand, is the opposite. Sound wave is slower in air. The speed is 330 to 340. You need to remember these values. But the same sound wave, when it starts to travel through water or glass, in glass, the speed is 4,000 meters per second. So imagine how fast. It actually travels much, much, much faster. Right? Now, you can ask me why. Why is it, miss, that the same light, when it goes from air to water, it slows down? But the same sound, it's also a wave, but when it goes from air to water, it becomes faster. What's the logic behind that, miss? The logic behind that is that light is a transverse wave. Okay? Now, when we talk about light, so light is made up of small particles, which we call photons. You'll study more about that in your A levels. Now, those photons, basically, when they travel from a less dense medium to a more dense medium, what is going to happen? There is more obstruction in its pathway. In air, the molecules are small and they're far apart. In water, the molecules are a lot closer, right? You must have done in chemistry, you must have studied about states of matter. In state of matter, you must have done solid, liquid, gas. Gas, the molecules are far apart. Liquid, the molecules are close together. So that photon light wave, when it travels through water, it's going to deal with a lot of obstruction in its pathway. So it becomes slower. But when the sound wave travels from air to water, it becomes faster. Why? Because sound wave travels by the vibration of the molecules. So when it's traveling through air, it's the air molecules that are going to be vibrating. In the light, it's not the air molecules. In the light, we have the photons that are vibrating. In air, it's going to be the air molecules that are vibrating. In water, it's going to be the water molecules that are vibrating. Because water is liquid, so it has got more molecules. So they will vibrate even more. They'll vibrate faster because there are more molecules to actually transfer the energy. So remember this, that a light wave, right, it becomes slower and as it goes to a more dense medium. Sound wave or longitudinal wave becomes faster as it goes to a more dense medium. The reason for that is because of the type of wave. Light is a transverse wave. So a transverse wave is one single particle that is vibrating. So when it goes to a more dense medium, it has more obstruction. It has, more molecules coming in its path. But a longitudinal wave is not one particle moving up and down. It's the particles of the air and water. They themselves are moving. So in air, less particles, less movement. Water, more particles, more movement. So sound wave travels faster. Right? So just remember this important distinction and the values. Follow me so far? Anything that's not making sense?
No, it makes sense.
Okay, all right. Now,
This
another,
is like
yeah, go on.
this is like a little harder than like light waves though.
It's, yeah, I know it seems complicated, but don't worry about it. You'll get this is the questions on it are generally pretty easy, and they are in sound. The questions are pretty same, right? In Okay, so like sound wave is just a bit more theoretical. Light waves was a bit, numerical calculations formula. This is just a bit more theoretical. There are not too many calculations in it.
So is it just like the opposite of light waves?
Just over here, just in this.
Oh, okay.
Yeah, just in this. And the definition. In the definition, if you remember, definition was something we did in the first class, right? So if you remember in the definition, I had taught you that in a transverse wave, the particles will vibrate perpendicular. They will vibrate up and down, right? If the wave is traveling from left to right, the particles will go up and down. In a longitudinal wave, the particles will not be going up and down, they will be going parallel. Meaning that if the wave goes from left to right, they will also be vibrating left to right. So that is opposite, and this feature is opposite. Okay? And pretty much we're almost done with the topic of sound wave. There's just one small thing left to discuss. That's it. And you'll actually, I think you'll find out that the questions on sound are actually not as complicated as it seems theoretically. They're not too hard. They're quite simple and they're the same kind of questions. Questions on sound are generally pretty much the same. So once you figure out how to solve one question, the rest of them are pretty easy. Okay, now I'm going to tell you two more definitions. One definition is pitch. Okay, what is pitch? Then, okay, now pitch you must have heard of if you are at all into music. You must have heard of the term pitch a lot, right? So, oh, she has such a high, or even generally, you'll be like, oh, she has such a high pitch voice. Or, oh, she has such a high pitch of a voice, right? Or you like if somebody has a deep voice and say, oh, they have such a low pitch. What is pitch? Okay, the pitch is quite simply put the frequency of the sound wave. Okay, what is the frequency of the sound wave? That's what a pitch is, right? So if for example, if you look at your musical instruments, so we have something like, let's say, a bass, right, or a cello. If you've ever listened to these musical instruments, they have a very sort of deep, like a deep melody. A bass is going to be, if you ever listen to a bass, it actually produces a very deep, right? So the reason for that is because the frequency is low. Okay, the sound waves frequency is low. What is frequency? The number of waves per unit time, right? So there are less number of waves being produced per unit time. Similarly, if you look at a violin, sometimes the violin, the musicians play really high notes, right? So the high notes that we are hearing is the frequency, okay? So basically, when you play a musical instrument, different sounds that we hear is simply the different frequencies, okay? So a high pitch is a high frequency. Now, I do not want you to confuse pitch with loudness. Okay?
So it's not loudness.
Yes, it's not loudness.
It has nothing to do with it.
It has nothing to do with it, right? I can talk in the same pitch, but so think of it this way, that a singer can sing the same note, but they can sing it loudly and they can sing it quietly, right? You can talk, if you try to talk yourself, you can talk in the same tone, but in the same tone, you can make yourself louder or um, uh, or quieter, right? You can talk in the same tone. So the tone, the frequency of your voice, right? That is pitch. Okay? So you can have a high pitch or you can have a low pitch, right? That's pitch. So my frequency of the voice is changing. Loudness would be if I'm talking in the same frequency, but my voice is getting louder, right? Louder, quieter. I'm talking in the same voice, same frequency, but my voice is getting louder or quieter. So don't confuse frequency with pitch. Sorry, loudness with pitch. Pitch and frequency are the same thing. Okay, so the if a voice, if any sound wave is going to have a low pitch, so it's going to have a low frequency. If it's going to have a high pitch, then it has a high frequency. Okay, loudness is related to amplitude. Remember that. I will draw a diagram and explain this to you. You remember the go back to the first chapter that we did, introduction of wave, right? Now, what happens is this, that if a voice has low frequency, it's going to maybe look something like this, okay? This is low frequency. So less number of waves per unit time. So in 1 second, I'm only getting one wave, okay? Now, this is low frequency. High frequency is going to look like this. See, so now there are three waves in 1 second, right? This is low frequency. This is low frequency. So this is low pitch. Okay. This is high frequency. This is high pitch. There are now three sound waves being produced in the same 1 second, right? Now, what is loudness? Loudness is this. Do you see how the number of waves are remaining the same? Okay. In 1 second, the number of waves are the same. Both waves are giving you the same number of waves. Both of them are giving you one wave in 1 second, right? But the amplitude of this wave is much larger. The amplitude of this wave is much smaller. Okay? So larger the amplitude, the louder my voice. The lesser the amplitude, the quieter my voice. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch, right? So loudness is related to the amplitude of the sound, while pitch is related to frequency. How many waves are we getting?
What does this say? Oh, sorry. Wait. Oh,
Okay, sorry, I got disconnected. 1 second, let me share the screen with you again. But yeah, is that making sense? What is the difference between frequency and sorry, pitch and Amplitude, is that all clear? What we've discussed so far?
Sort of like, so loudness is based on amplitude, not the frequency.
Yes. Yes, correct. And frequency is what? Frequency is related to the pitch of the sound. Okay. Last things that we have to talk about related to our topic is that we just have to talk about an experiment that is often used to measure the speed of sound. So you get questions in your past papers where they say devise an experiment or plan an experiment, or how are you going to determine the speed of the sound. You saw those experiments related to light waves as well, right? Like there were questions on how will we do it for light waves. So similarly, you get questions on sound waves too. So let me just tell you how exactly are you going to figure out how the sound wave is going to work. Just give me 1 second. All right, so now what is the experiment that if they ask you in the exam that you are going to go ahead and you are going to travel, or that you are going to explain, okay? The experiment that you do is that you can, okay, now there are multiple ways of doing this experiment. You can do the experiment either by using some a microphone and a receiver. You can do it like that. You can do this using your friend. I'll tell you the easy way, but there are multiple ways. Okay, if we come across questions in them in the past papers, I'll explain other methods, possible methods too. Okay, we will discuss given questions. We'll discuss what are the different methods we can use. Okay, but mainly speaking, one of the methods that you can use, the easiest one is that you, this is you, okay, and this is your friend. Now, what you have to do is that you have to make sure that you and your friend are standing far apart from each other, at least like 50 meters. Okay, at least 50 meters apart, maybe more if you want. Now, what um now over here you can go ahead and you can do multiple things. One thing that you can do is that you can fire a gun into the air. Now, what's going to happen that when the gun is going to you're gonna fire a gun into the air. Okay, the moment you fire the gun into the air, you start your timer. Okay, you fire the gun, you say you have a timer in your hand, you start the timer. Okay, now the sound wave is going to travel to your friend. When your friend hears the sound, when they hear the sound of the gun, at that point they will signal you and you will stop your time. Okay, so you will go ahead and you will stop the timer. So start, you shoot the gun and you start the timer. The wave reaches, the moment your friend hears the sound wave, they'll signal you and you'll stop the timer. Okay. Now, what are you going to do? You know how long it took for the sound wave to travel from you to your friend, right? You know the distance. You know exactly how far away your friend was standing from you, right? You know exactly how far away your friend was standing from you. So what you can do is that you can simply use the formula speed is equal to distance over time, and you can calculate the speed of sound, right? You can do this in multiple ways. If you want to be more accurate, you can take a microphone, right, and a receiver. Okay. Now, what is going to happen that you place the microphone in front of, for example, you take the microphone in your um you take the microphone, keep it with you. Okay. Now, far away from you is a receiver, something to pick up the sound wave. Okay. So you speak into the microphone and then you see how long it takes for the receiver to get the sound. So these receivers are usually attached to a computer. You attach these kind of receivers to a computer. So it will automatically record how long it took for the time to reach. The point is, the main point of the experiment is that there should be someone to produce the sound, someone to receive the sound. You always note down how long it takes for the sound to travel. The distance you will know because you decided on the distance. You're going to tell your friend how far away to stand. You simply put this in the formula and you can find out the speed of sound. That's it. There's nothing much to the experiment. You can do multiple ways. You can do it in multiple things. There are lots of ways of doing it. This is the easiest way. You take yourself, you take your friend, you make your friends stand far away from each other. You can shoot a gun, you can shoot a flare, whatever you like. And when your friend hears the sound, you stop the stopwatch and you record the time and apply the formula. Or you can use computers. You can use a microphone and a receiver that's connected to a computer, and the computer will do the same thing. Regardless, the principle is the same, right? Making sense?
Yeah.
Okay, perfect. Now, the last thing that I have to tell you is, remember one more thing. Sound requires a medium to travel. What do I mean by medium? There should be some kind of particles present. Okay. Why? Because for sound waves, for longitudinal waves, I need particles. Sound travels through air because of vibration of air. Because the air molecules are vibrating, that's why sound is traveling. Because the water molecules are vibrating, that's why the water molecules are that's why the sound is traveling. So with the for a sound to travel, we need some kind of medium. Okay. That is the reason there is no sound in space. There's no sound in outer space because in outer space is a vacuum. Vacuum means that there are no particles over there whatsoever. So because for the sound wave, we need medium, there's no sound in vacuum. But light can travel in space. Light can travel in a vacuum. And why is it that light is able to travel in a vacuum? That we will discuss when I teach you about the electromagnetic spectrum, right? But the main thing to remember is this, that light can travel in vacuum, it can travel in space, but sound waves cannot. Why? Because there are no particles in the space. It's in a complete vacuum. Right? All clear?
Yeah.
Any question, any part that's not 100% clear, anything that's not making complete sense?
Would there be a question like to state the independent dependent variable in that question for like the experiment or no?
Yeah, you can get it, right? You can. And you can even guess. Can you think of the independent dependent variable over here in your experiment?
Um, that what?
Technically, in this experiment, yeah, you can have an independent and dependent variable if you want. Not
Oh, okay.
necessarily, because we're just doing a calculation, right? But if you want to, you can have an independent variable and dependent variable. What is going to be your independent variable? The distance, right? The distance is in your control. You decide how far away your friend is. Is she 50 meters away from you? Is she 100 meters away from you? How far away is your friend? That you can control. But what are you measuring? The time taken. The further away your friend is going to be, the longer it's going to take for the sound to travel, right? So, if you wanted to do an experiment, so an dependent variable and an independent variable is would be more effective if you were doing an experiment. For example, what is the relationship of distance and time? Then yes, it would make sense. But in this experiment, we just want to calculate the speed. So that's why we want the values. So technically, there's no need for dependent or independent variable. But if you do need to give the answer, they're not going to ask that. But if they do, or you need to discuss it, time is your dependent variable, distance is your independent variable, because you can control how away the person is, but the time taken is going to be depending upon the distance, right? The further away the person, the more time it's going to take. So distance is in your control, time is something you have to measure. Time will be dependent and distance will be independent. But in this experiment, we don't need to mention that. Okay, the reason we don't need to mention is that because we don't need to take multiple different values, right? We just need one value of distance, one value of time, and that's it. If you do take multiple values, then you can take out the average, and that will just make your answer more accurate, right? If they ask you how you can improve the accuracy, you can say take multiple readings and take out the average. Okay, does that answer your question?
Yes. Thank you.
Okay, all right. Okay, so Sasha will go ahead. We'll stop it over here for today. And now in our next class, we're going to go ahead and take a look at questions related to the topic of sound. Okay?
Okay, thank you.
Okay, all right. Thank you so much, Sasha. See you next time. Have a good day.
See you. You too.
Bye.